So welcome back, everybody. 2 weeks away. Seems like forever, doesn't it? It kind of does. It's like, wait, this isn't January? Like we have to finish this semester still? But sadly, yes. So when we talk about finishing the semester, we have 2 weeks of classes left. I posted today what is likely to be your very last lecture and example. We're doing interactions with categorical predictors. That'll take a little while. So I'm not anticipating we'll be able to get to anything else. The other thing that we have left is a quiz that I will put up after class, probably on Thursday, so we can go over that on Tuesday, and one more homework. So your homework, I've decided, is going to be about the interactions among quantitative variables that we started and are going to finish today. That way, you will be able to finish your homework before the end of classes and wave bye-bye to this class. How's that sound? Does that sound good? All right, I will let you know when that's up. I hope to have that up tomorrow. One other thing that I typically do, so I have on here time for course evaluations. At every other university I worked, they were still paper evaluations like Scantron sheets, and so I did a supplemental evaluation via Qualtrics with more specific questions. And I had previously given each person who completed my supplemental evaluation an extra credit point for doing so, because I rigged Qualtrics to be able to tell me which person had done it, but not what their answers were. However, at this university, I was happy to see allows you to add your own questions to the electronic response things. And I thought, great, okay, I'm going to do the Qualtrics questions in here. But then I realized it doesn't tell me who answered the evaluations. So here's the deal that I want to propose to you guys. I had to check my enrollment here. This class has 15 people officially enrolled. If I get at least 13 of you to complete the evaluation, I'll give everyone a point of extra credit. Okay? So don't let your teammates down. And as stated in the email announcing that evaluations were open, I will give you time on the last day of class to sit here and fill them out. They encouraged me to do that, and I thought, sure. So if you come to the last day of class, to finish the last example, you'll have time to complete those, and you'll get 1 extra credit point if at least 13 people do. How's that sound? Deal? Okay, so this is the very first time I have taught this particular class and these particular materials. I'm going to be doing it for the foreseeable future. So your feedback is going to be critical in helping me decide how the course should change and adapt. So please be as honest as possible. You won't hurt my feelings. You can say, I love this part, but this thing you had me do was pointless. Okay, great, that's useful feedback. Not useful feedback would be, I didn't like it, or it was okay. That's not useful, right? I can't change anything based on that. So please be as specific and honest as possible. The rest of the cohorts are depending on you. All right. Next semester, I have, I think, 11 people in this class again, and then the other one, the generalized class, has 17 last I checked. 18 now. Let me see here. Spring 2020. We'll check my enrollments. You're the 18th person, yeah. So all my plugs for come back next semester must have worked, at least a little bit. So I'm excited about that. I believe I am winning the quant sweepstakes of advanced classes in terms of the enrollment. So. And Selected Apps now has 15, so just as many. So yeah, it's we're gathering steam here. Okay, so what I had wanted to do today is sort of bring us back to the world of interactions, answer any homework questions that we hadn't had a chance to answer, and just sort of do a general kind of review, bring us back before jumping into new stuff. Does that sound like a plan? I don't have a specific agenda, but just making sure that we're all sort of back on the same page seemed like a good idea, especially after Thanksgiving brain. You know, you get away from something for a while and it sort of flies away, right? But let's see here. So I have open a copy of Homework 5. So are there any questions that you have specifically about that you want to go over, or would it be helpful if I just sort of went over most of it? Or none of it? It's your call. Question 2? Option 2. All of it? You got it. Thank you for speaking up. So each of your homeworks, I'm trying to do something a little bit different and build on the skills that you have. This one was the idea of a hierarchical set of models. So you're adding predictors to see what happens to the predictors that are already there. That way you can see what predictors still have unique effects after controlling for other things. So this particular homework had more models, but it didn't require much information that wasn't produced to you already by the output. So let's see here, empty model. So in your life, would you ever run an empty model for a general linear model? The answer is no. So this first step here is purely pedagogical. What I want you to be able to recognize is that what models are trying to do is predict an outcome's mean and its variance. So if you put nothing else in the model but the outcome, everybody gets the same mean, which is given by the fixed intercept, and all of the variability in the outcome variable is labeled residual variance. That's the most that there is to be predicted. So it's a benchmark. In more complex models, such as mixed effects or multi-level models where there's multiple kinds of sampling and therefore multiple kinds of variability, this empty model is a very important first step to try and partition the kinds of variability that you would see across different levels of sampling. So this is sort of foreshadowing what you will eventually be doing if you stick with more advanced classes. So then this is sort of definitional review down here. The intercept, if you have no predictors, is the overall sample mean. The intercept standard error, otherwise known as the standard error of the mean, that's the average distance of the sample mean from the population. So even though we only have this one sample, we're using the sample's mean and variance to try and extrapolate what the variability of the mean across samples would be. So it's one of those you just kind of have to believe, but that's what statistics is all about. It's about using probability distributions given one sample to try and make inferences as to what would happen. Let me turn this off here. All right. The variance, so it's labeled residual variance or mean square error, even though in this context it's all the variability that there is to be had, is the squared average distance from the mean. So things like standard deviation and standard error, those are in unsquared units, in the units of the original variable. Variance and I guess it's the sampling variance of the fixed effects like the asymptotic covariance matrix, those are in squared units. So there's an asymmetry there that shows up across different kinds of models. So that is sort of your jumping off point. Then we added our first predictor. So after adding motivation, enter the amount of outcome variance that is unrelated to motivation. So I'm deliberately trying to use different terminology to get you to recognize other ways of describing the same phenomenon. So what am I asking for here? The amount of variance in the outcome, which is, I forget here, ratings, that's this one. Yes, performance ratings, and the amount of variance in performance ratings, that is unrelated to motivation. What am I asking for here? Residual variance, so leftover variance, that's what residual means. The part of the variance, the amount of the variance that is unrelated to motivation. So previously, the residual variance, which was all the variance, given that this was the empty model, and this person's homework was 277, it went down to 259. So 259 is what's left after controlling for motivation. So at this point, each person's predicted outcome would be based on their X value for motivation, such that any two people who had the same level of motivation would have the same expected outcome. So you can think of this residual variance as the squared average deviation from the regression line that is predicted from motivation. Okay, that works out to be about a 7% reduction in variance. So the proportion of variance accounted for by the model. It's technically based on sums of squares, but it's pretty closely approximated as the proportion that 259, the difference between here. So it would be 277 minus 259 over 277, roughly, will be this number. It won't be exact, but it'll be very close. And in more advanced models, that's how we usually do it, because more advanced models don't use sums of squared as their estimation approach. Test statistic. for the proportion of variance accounted for by the model. What am I asking for here? F, very good. When is F and T the same? When are F and T the same? Let me back that up. How are those related?
T squared is F.
T squared is F. So when could I use a T here instead?
Is it one predictor?
Yes, one predictor. So a test statistic for the proportion of variance, I'm asking for F because I said model. But you could enter T squared and that's the same thing here. So if your one predictor is significant, then your model is significant, then your R square is significantly greater than 0. There's a one-to-one correspondence there. So if all I cared about was the relationship between motivation as a predictor and performance as an outcome, can you think of a more simple way that I could answer that question if that's all I wanted to know? Does motivation relate to performance? Did you learn something earlier in the semester that might have answered that question simply and directly? Mm-hmm. Correlation, yeah. A bivariate relationship, because that's all we have in this model. So R, if I have the correlation between these variables, if I do R square, that's R square. Literally. R is the square root of R square. That makes sense? Yeah. So this entire thing here is essentially redundant with a correlation for all intents and purposes because it's just telling me the same thing. It's telling me that 7% of the variability in performance is accounted for by motivation. I'll make you do math in your heads. That means the correlation would have been what? I have Excel out, I'll cheat. 0.07. That's R square, right? So what if I want to get the correlation? What do I got to do? Square root. Okay, maybe you can't do that in your heads. How about that? I know I can't. But yeah, so the correlation would have been about 0.26. Within rounding error, that translates into an R square for variance accounted for of 0.07. Okay. The intercept. Let's see here. So this p-value for the significance test of the model is asking whether or not F is different than 1, because it's a ratio of what you know to what you don't know, whether the R square is greater than 0. Note that the p-value that's given down here for this answer is exactly the same. That's not a coincidence, because the p-value for the significance test of the model of the R square should be the same as the p-value for the significance test of the slope that created the R square. So this is the p-value that goes with the t for the slope of motivation. And the t-value would be the slope's estimate divided by what? How do I get a t? Do you remember? Your first column is estimate, second column is something, third column is t. There it is, standard error. That's the one below it. So estimate divided by standard error gives me the t. And I didn't ask for the t in this case, but the p-value is based on the t. So what does a p-value of 0.0002 indicate? Significant. What's my cutoff for significance? Less than 0.05. Did I just make that up? It's what everybody uses. Somebody made it up and we all agree with it. So what does that mean in practice? A cutoff of 0.05 means we're willing to accept what? Type which? There's two kinds of errors, right? 1 or 2? So which one is this one talking about? Type 1. What's a type 1 error? False alarm. is either a false alarm or a miss. This one is the false alarm. So if we say a priori that we're willing to have a cutoff of 0.05, in other words, we're setting our alpha at 0.05 for our type 1 error rate, then we are saying 1 in 20 times, or 5% of the time, this level of result, the slope this big, but the standard error this big, would arise by chance, if the null hypothesis were true. So if there really was no correlation between motivation and performance, we would see a t generated by estimate over standard error that big, not very much of the time. 0.02% of the time. What's the other kind of error? Beta, which is type 2, which is?
It was there, but you didn't get it.
It was there, but you didn't get it, or miss, right? Yes. So do I have to worry about that in this context? No, I declared significance. So the only kind of error that I have to worry about is type 1. If I had declared non-significance, then I'd have to worry about type 2. I'd have to worry about missing something that I said was not there. All right. So the slope estimate itself, let's talk about the regression line here. So the regression line has an intercept of 54 in this example. What do you have to have right to get the fixed intercept right? Centering, what does that mean? I'm hearing mumbling. Say it louder because you're correct. Say it with authority.
An intercept that makes sense?
An intercept that makes sense. That's why we do centering. What is centering?
Shift the data.
Shift what over?
The
The outcome or the predictor?
predictor.
The predictor. Yes, so data, too vague. Predictor, you got it. So we shift it over by adding or subtracting a constant. It's usually subtracting because we're usually dealing with positive numbers. If you were dealing with negative numbers, you might have to add something. So in these instructions, I gave you the centering constant that I would like you to use, which in terms of motivation was a centering point of 4 on a scale of 1 to 7, which meant I'm fine with doing that. Did you like this? The motivation to kick ass in graduate school, the MCAGs. 1 was, I will totally hate that. 4 is, I am fine with that. And 7 is, I will totally love that. So that's my scale. So I asked you to center at 4. So that's the only way you would end up with the correct intercept. Now, is there a wrong way to center? What would have happened to my model and my significance of the effect of motivation had I just left it uncentered?
Be weird.
It'd be weird. Would it be wrong, though? No. I'd still have the same R squared. I'd still have the same significance for this slope. What would change is the intercept. So centering is an interpretational option. I picked 4 because it was in the middle. The mean of the variable, when it's not exactly in the middle, would be fine. The minimum is fine. The maximum is fine. Now, where that starts to matter more is if motivation was part of an interaction in the model. Because then the predictor of the interacting variable, its slope would be specific to where motivation is 0. And then it gets even weirder to have a nonsensical 0. Okay. So a positive slope then, so the intercept is 54. So an average rating is 54 for somebody with a motivation of 4. So how to interpret a slope? The bare bones is always the same. For every unit change in x, y goes up by blah, right? So for every additional unit of motivation, performance goes up by 3.7. And that is a positive number, which means then that more motivation is associated with higher performance. Can I say more motivation causes higher performance? No. Someone will yell at you if you say that, and rightfully so. Because unless you have a causal design, a design that permits causal inference, you don't know what causes what. So you can say they are related, they are associated, any of those sort of words that just imply a relationship that's it's bidirectional or non-directional rather, that's cool. All right, with me so far? All right, next, GRE scores in the old scale. So this is my version of what I think the GRE is worth, which is, you know, next to nothing, but that's a whole separate class. By the way, I once did a presentation on these GRE scores in the old scale that went from 200 to 800, where the mean was supposed to be about 500. And if you dig deep enough into ETS's website, they have a pamphlet that's called the Guide to Interpreting GRE Scores. Would any of you like to guess what the standard error is for a score of, I believe it was 550 on the quant test? Would anyone like to guess? It was 50.
Oh, geez, wow.
It was 50. So let's think about standard error, right? It's supposed to be the average distance. So if you wanted to form a confidence interval, like a 95% confidence interval, you would take 1.96 times 2 standard error, or 2 standard errors basically. So basically what that means is that if you got a score of 550, your expected score, if you took the test over and over and over again, like if you're the population, would be somewhere between 450 and 650. That is the level of precision the year that I looked this up. And even better is that that precision was created via a simulation. So that is the absolute best case scenario of standard error, and it's still that big. So for any of you who didn't ace the GRE, who the hell cares? There. That's also one of the things that I tell folks when they ask, like, I have this student who did really bad on the GRE. Can I say something in my letter? I'll be like, point them towards the Guide for Interpreting Scores and ask them to figure out what the standard error would have been. The reason the standard error is not reported in the test, by the way, is because not everybody gets the same items. And so it would have to be based on that. And also because it's bad for business to know just how unreliable the scores are. So anyway, off my soapbox. If you're interested in measurement and how unreliable scores are, next fall I am teaching factor analysis and structural equation models, which is a class that I get to do here for the first time. So it will have confirmatory factor analysis, item response models, and SEM sort of as one package coming to you next fall. And if you come back next spring, if you learn what a logit is, then you'll have all you need to know to be able to participate. So, plugging my courses, trying to keep the numbers up. Anyway, I missed you guys. I'm sorry. I'm really pumped. I haven't gotten to do this in 2 weeks. Okay, back to the story here. So I asked you to add 2 predictors. So GRE scores, which is just verbal and quant. At the time, when I took it, there was analytical, which then died and became writing. So I've never got the chance to do writing, but analytical was my favorite one. So variance left over, nope, just the 122 here. What am I asking for again? Residual variance, otherwise known as, what is it called in your output? Not SEM, other way around. Mean square error, yes. So I say that because when you're using analyses where least squares is your estimator, which is what all this stuff is, it will be called mean square error. When you use analyses based on other estimation techniques, it will be labeled residual variance instead, more direct. So enter the proportion of variance accounted for by the model. What am I asking for here? R square. The test statistic for the proportion of variance accounted for by the model, what letter? F. Could it be t squared instead? Not anymore, because 3 is my numerator degrees of freedom. That means that I am testing 3 slopes, their joint contributions simultaneously. So this test statistic is based on not only their unique effects, but subtracting what they have in common. So R square takes into account all of that. So F is a multivariate test that takes into all of that. Denominator degrees of freedom, where did that number come from? I know it came from your output, But like, where does it come from more generally?
Everything else
Everything.
without the numerator.
So where does it start? Where does it start? So I ended up at 196. Where did I start from? What's the highest degrees of freedom I could have in this assignment? Say it louder.
97?
97?
That's what I said. I said 199, then I changed it to 197.
199 is correct
Yes.
because I had 200 people. So the -1 is for what?
Intercept.
Intercept, because I need the intercept or the mean to be able to calculate variance. So 199 would be the degrees of freedom for the empty model. I added 3 slopes, that breaks me down to 196. So how many more slopes could I have before going bankrupt? 196. Yeah. So that's what that means. It's like points left over that you didn't spend. So this is the p-value that goes with F. The change in the proportion of variance accounted for due to GRE. So that is, I have an R-square currently of 0.56. It used to be 0.07. So 0.56 minus 0.07 is my 0.4966. So that's my change in R-square. Enter the test statistic for the change in R-square. Okay, this is one I had a lot of questions about. What letter am I looking at here? Test statistic for the change in R-square. There's only 4 choices. There's T, F, Z, and chi-square. And Z and chi-square went out the window a long time ago.
I'm going out.
You're going F, yes. Do you know why?
No.
So in this case, it has to be F because we added 2 slopes. So this F value is created by combining the 2 slopes that we added to see if their joint contribution increases the R-square. Had I only added 1 slope, then that T squared would be equivalent to my F. So the difference between this F, the 85, and this F down here, the 112, the 85 is the proportion of variance accounted for by the model, all 3 slopes together. The proportion of variance newly accounted for, the change in R-square, by the 2 GRE slopes, that F is higher. F is like per slope. So if you take 7% as 1 and 49% for the other 2, the other 2's contribution, like per slope, is much higher. Motivation did not contribute as much as GRE. So when you lump them all together, motivation actually brings down the average contribution. So numerator degrees of freedom for the test of the change in R-square is 2 because we're testing the addition of the 2 new slopes simultaneously. Denominator degrees of freedom is the same because we're just dealing with a subset of the same model. We haven't changed the model, so it still just has 3 slopes and 196 points left over, slopes left over. And this is the p-value that goes with my F. Okay, with me? Great. Fixed intercept. So what has to be true to get this intercept correctly? Correct. Same thing as before, but just more complicated. Starts with a C.
Center.
Yeah. So not just motivation set at 4, but the 2 new slopes have to be centered as instructed too. Otherwise, the intercept will be a different number as the reference point, as the "you are here" sign of the data. So I instructed you to center verbal at 500 and quant at 550. If you did so, you would get this number correct. So let's see first here. The fixed slope for verbal. Minus 0.0034 with a standard error of 0.03 and a p-value of 0.9. Putting that together, is the slope of GRE verbal positive or negative? Negative. So that means as GRE verbal goes up, performance goes down. Significantly or not significantly? Not significantly, yes. So this p-value right here, well within expected territory. So basically this slope is essentially 0. It's well within the part that is just noise. Because you know why? GRE doesn't, verbal doesn't matter in my world. That's why.
That really confused me. It took me a really long time. I was like, does it go down?
No, because I put a 0 value in the population, which means that for some of you it was a little positive and for some of you it was a little negative, right? They wiggle. But yeah, this is my world. This is my story world. I get to make it however I want. Because you know what? In simulated data, the people are really cooperative. However, quantitative, different story, right? So quantitative slope I built in to be positive. So for every unit more quant, your performance rating goes up by 0.46, significantly or not significantly? Significantly in this case, yes. Because I believe that quantitative ability does help you in graduate school because it makes you have these courses be easier. All right, motivation. Positive slope, in this case, still significant. However, if I compare it to the slope that we used to have, the slope where motivation was by itself was 3.7. The slope where motivation is paired with GRE scores is reduced to 2.5. What do you think about that? What would I conclude based on that difference? What's the difference in how I would talk about the effect of motivation?
Motivation when controlled for with GRE scores.
Yes, this is the slope for motivation controlling for GRE scores. Give me some synonyms. That's probably my preferred way. I'll give you one, a word that starts with U. U-N-I-Q. Yeah, this is the unique effect of motivation controlling for GRE scores. Can you think of any others? The effect size, one of the effect sizes you could give would be a semi-partial correlation, which is the correlation of motivation and performance after controlling motivation for any covariance with GRE scores. So controlling for, adjusting for, net, sometimes people say, net GRE scores means controlling for. Any of those words would be fine. Just pick one and stick with it. Remember, no synonyms allowed in your results sections. Just pick one and go with it. It makes it boring and formulaic and therefore easy to read. Yeah, so it's still significant, but it looks like it matters less. And yes, if we wanted to talk effect size for these things, we have several choices. You could ask for standardized slopes to go with each of these slopes. What are those? Standardized means what is the new scaling of the predictors and outcomes?
Mean is 0.
Mean is 0 and
Standard deviation is 1.
standard deviation is 1. In other words, they become on a z-score type metric. So z is back just for a minute. Yeah, and so if you standardize your predictor and outcome to a mean 0, variance 1. So you can do that in your data manipulation. You can enter those standardized predictors in the model, and the slopes that you get will be the standardized versions. You can also ask for them as a separate command. And so that is a fairly common way that people address effect size in regression models. Another approach you can do is semi-partial R-square. Remember that one? Nope? Ish? Yeah, so I learned a lot more about that actually over the last 2 weeks. So semi-partial R-square is supposed to be the part of the R-square that is uniquely attributable to that predictor. Supposed to be, because it only works out that way for quantitative predictors. It does not work out that way for categorical predictors. So we'll return to that as put a pin in that, so they say. But I've fallen out of love with that as an effect size because of that problem. Semi-partial correlation would be semi-partial eta squared's square root. Those two are related. That's another thing that you could do. You could also compute out of the t statistic a d or an r. So in your example 6, I think at the end, I had a table of all the different effect sizes. You just got to pick one, say how you computed it, and go with it. They'll be related to each other. They'll be very similar, but not exact. So each individual slope would have an effect size for its unique contribution. The effect size for the model is given by the R-square for the model. Each individual slope has a t statistic and a p-value that goes with its unique contribution. The joint contribution of all of it together, also taking into account any collinearity, the covariance between them, is given by the f value for the R-square. Okay, let's see. Yeah. So this part down here was just asking to make sure that you keep track of what a difference is. When you're interpreting these coefficients, you always have to keep in mind that they go with a unit. So you can't say something like, for this one right here, let me give you an example of a wrong sentence. As GRE quantitative goes up, performance goes up by 0.46. What's wrong with that sentence? I'll say it again. As GRE quantitative goes up, performance goes up by 0.46. By how much? Yeah, I did the how much for half of it. So it's as quantitative goes up by 1, performance goes up by 0.46. Or you can say as quant goes up, performance goes up. So you have to give the units on both sides or neither side. If you have a table that has this information, it's fine to say as quantitative goes up, performance is predicted to go up. So it's up to you whether you want to throw the coefficients in there. I would if they're not being reported elsewhere. Let's see. Any other questions on that one? Okay, the last one here. So same principle, different context. I asked you to put in fear of statistics as a ordinal predictor, little, moderate, or severe, and see to what extent that predicts performance. So this variable has 3 categories. How many predictors, their slopes I should say, do I need to include to fully capture the differences between these 3 categories? Got to vote for 2? Why 2? Why not 3? Because there's 3 possible mean differences here, right? There's little versus moderate, little versus severe, and moderate versus severe.
Well, moderate versus severe is a linear combination.
Yes. The third one is going to be a linear combination of the other 2. In other words, if you have an intercept in the model, that's going to become the expected mean for whichever is your reference group. And you'll only need 2 other slopes to show the other 2 differences because the third is a linear combination. Now, I tried to shake things up in this case and asked you to do a different coding scheme. And I interacted with several of you about this, so I wanted to show you what your choices are in terms of doing this. So we have little, moderate, and severe. And I had asked you to do little versus moderate and moderate versus severe. Just change it up a little bit. Many of you on your first pass did this instead, little versus severe, because what you ended up doing is putting zeros where little is, which is correct, putting a 1 here, which is correct, and then putting a 1 here. this up here. So the way that I named these is because if you use this coding scheme, the first contrast lumps together little and severe and contrasts moderate versus that lump, and the second contrast spreads out the lump into little versus severe. So if you coded it this way, you could still get the answer for what is moderate versus severe, but it would have to be a linear combination of the second slope minus the first slope. So how many of you did it that way? Fine, right? It works. So therefore, it is correct. Now, what would I have to change to make the contrast directly give me the answer that I requested instead? Well, 1 still goes here. If I want little to be my reference group, 0 goes here. So it's this quadrant that I have to worry about. Think about lumping. I want to be able to pull apart moderate versus severe, which means this needs to be a 0 because this one is going to become severe. This one actually needs to become a 1. So now the first contrast is little versus moderate severe as a lump. The second contrast comes in and splits moderate versus severe. And so now the first one is little to moderate and the second one is moderate to severe when they're paired together. So that would have given you moderate to severe directly in the model. If you had wanted to know little versus severe, that would be a linear combination of this version. Either way, you're going to end up with the same R square, the same test of the joint contribution of these two contrasts, and you're going to end up with the same intercept because either way, little is the reference. So which one of these is more convenient would be the thing you'd want to settle. Dummy coding, this version where you use this one, fit that back with this one. There we go. That one and that one, that's by far the most common approach. But it's up to you how you code these things. And so this actually foreshadows why it is that semi-partial correlation breaks down for categorical variables. Because each of these possible differences, little versus moderate, moderate versus severe, and little versus severe, has a different semi-partial R-square that goes with it. And the three added together are more than the two contrasts if you put them together properly, because they're collinear. Because because little is a common reference group. They overlap. So semi-partial correlation doesn't work for the individual contrasts. It should work if you put them together. And so I'll show you more about that in example 8. But if you had done your coding the way that I did, which is that, hang on, yep, that's how you would have gotten the right answer directly. But it's still right if you did it as a linear combination. And in terms of the interpretation, I said it so that little versus moderate, more fear decreases performance, but non-significantly. But a lot of fear really decreases performance. I would call that the stab yourself in the foot phenomenon. But you guys aren't afraid anymore, right? Not anymore. We're in the home stretch. So, and you're coming back for more. So, how awesome is that? I had questions on Friday before Thanksgiving about what I meant by shift. I just meant a difference. That was all I was going for. I didn't mean to confuse people with that, so I'm sorry. The questions alternated what was the reference. So moderate to little versus little to moderate. I was looking to make sure that you understood which direction the coefficients took. So if little is the reference group, and it's little versus moderate as the contrast, then the moderate is the one who picks up the amount. So if the coefficient is negative, that means moderate is less than little. If the coefficient is positive, moderate is more than little. So shift from to was meant to imply directionality. So if there's a way that I could have said that more clearly, I'm all ears. Because I wanted to not say difference between, because that to me was ambiguous as to what the direction was. So I settled on shift. All right. So, any questions? All right. So all of these effects in here, slopes is sort of the generic term. These effects I would further categorize as marginal effects or unconditional effects. So let me get out my little vocabulary sheet here. So we have, like, at the highest level of the hierarchy here, fixed effects. And under fixed effects, they come in kinds of intercept and slopes. And then under slopes, they come in a kind of either, let's go with marginal versus conditional, main versus simple main. And so everything on this homework was in this column right here. It's the idea that even though the slopes are unique, let me add that as a layer, actually. Let's see. I'm trying to figure out how to do this on the fly. I should learn better. Here we go. There we go. Okay, now I got it. Here's my vocabulary tree here in Excel. So all of these things are fixed effects. Fixed effects just mean a constant, that everybody in the sample gets the same of it. So if I have a beta 0, everybody gets the same beta 0 applied to their score. So that would go with intercept, right? B0. Slope is also a type of fixed effect, but this is, the change in y over the change in x specifically. So it's a different kind of fixed effect, and so it'd be beta 1 plus usually. If I only have one slope in the model, then that slope is a marginal effect or a main effect, meaning that that is the slope for everybody. If I have more than one slope in the model, then I have to use the word unique. Each slope is its unique effect after controlling for the other slopes. When a given predictor only has one effect of itself in the model, it is not part of an interaction, such as in your last homework, then you're in this column. All of the effects are unique after controlling for the other ones in the model, but they are constant for the sample. They are marginal, or what I call main effects. So like if the slope for motivation is 3.4, it's 3.4 for everybody. It's not 4 GRE equals this, or 4 people in the low fear group, because they don't interact. When we get over into the last column, that's where if you have two predictors in a model, so let's say that we had motivation, we had verbal GRE, and we had motivation by verbal. Model like that. Each of these effects would be unique in that it's controlling for the others. But motivation and verbal now take on this additional layer of being conditional or being simple, meaning that this is the motivation slope specifically when verbal is 0. This is the verbal slope specifically when motivation is 0. This interaction term is actually marginal in the sense that it doesn't have anything else it's interacting with, so this interaction is for everybody equally. So I stopped using slopes a while back because it wasn't specific enough. Now we're getting into types of slopes and whether or not they are conditional and unique or just unique. So Terry, I think you had asked about reviewing sort of this vocabulary. Does this help? Okay. So the conditional / simple is whenever you have to say for somebody of this certain type. If you don't have to say that, then it's just marginal and it holds for everybody. All right.
So the other half of my question then with it is, because everything gets the word effect. It's like simple main effect.
Yeah.
But these are separate when we talk about like effects, when we talk about like, what is it called, like beta squared and like
Those are effect
effect
sizes.
sizes.
Mm-hmm. Those are effect sizes because that term effect size means that there's some metric that is being used that everybody knows what it means. Most common 0 to 1, but these actually go from a negative to positive infinity, but it's in a metric that's in standardized mean differences, so it's correcting for differences in the scale of x and y. So yeah, effect is a generic term. It's basically useless.
Yeah.
And I say fixed at the top of all of this is because if you come back next year and I get to teach multi-level, there's going to be something called random effects, in which each person gets their own version of it. So I want you to already know that fixed effect is only one kind in a broader universe. So yeah, what is the effect of blah on blah? They mean fixed effect, but in order to answer the question, it depends on what else is in the model. So give you an example. I had a friend whose dissertation was looking at the effect of coping behaviors on psoriasis severity. So it's one of those diseases that's supposed to be somewhat psychosomatic in that like stress levels and emotion fluctuations and things have been shown to have some sort of relationship. And she was interested in forgiveness as a moderator of the effect of coping and stress on these things. And so she wanted to know to what extent people who are higher in forgiveness are better able to handle stress. So that was her primary aim of the study. So how would one answer an aim like that?
How should determine if someone is more forgiving?
She had a survey. It's called the Heartland Forgiveness Scale. That was actually my GRA appointment. I had a quarter-time appointment on that project, solely because a reviewer told them they needed to do a confirmatory factor analysis, not an exploratory, and no one knew how to do that, and they hired me. So I had extra money because I learned something in stats class. And ironically, because the forgiveness scale it's part of a world of a lot more people, that is my #1 highest citation with a bullet. Of all the papers that I've written, I was third author on the forgiveness scale, which is sort of hilarious. Because the lead author is no longer in the field, she's in private practice, the second author is dead, and so I get a request at least once a week from somebody wanting to use the scale or translate it into a different language, and I always say, fine, like, I'm not the forgiveness person here, I'm the factor analyst. Like, I can't help you. But anyway, so she had this Heartland Forgiveness Scale. It had some evidence for reliability and validity, and so you give out the scale and you sum it up, and that's your level of forgiveness. Okay, so we have a measure of forgiveness. Okay, so we want to handle stress. That means we need a measure of stress, right? So we'll call it measure of stress. I want to say she used a couple different ones. So she measured a construct in multiple ways because there's like objective stress versus subjective stress. And then handle. So she was interested in the effect of psoriasis, on psoriasis rather, measure of psoriasis. Her husband was a dermatologist, so that was super convenient to get some samples.
What was her N on this?
Oh, goodness. 160-ish, maybe it was. So yeah, it was her dissertation. It's in the annals of KU somewhere. So these are my variables, and my research question is: do people who are more forgiving better handle stress? I might be paraphrasing. I'm prone to do that, but it makes a good example. So psoriasis is the outcome in this case. So my regression equation, psoriasis equals, need an intercept, beta 0. How do I operationalize this idea?
Have forgiveness and stress, and then the interaction between forgiveness and stress.
I like that. Beta 1 times forgive plus beta 2 times stress plus, put this down, stop it. No, hang on. It won't let me zoom back out. Plus beta 3 times F times stress plus E. Okay. Which of these coefficients answers my question? And what direction should it be? Now picture yourself writing an analysis plan for your dissertation proposal or a grant proposal. And you're not allowed to use mamby-pamby language like moderate. You need to be more specific, because she had a specific idea here. So if each of these variables is measured, I can't spell forgiveness, told you I didn't know anything about it, such that higher scores equal more of the construct. So if stress is bad for you, what direction would you expect beta 2 to be? Do you think forgiveness is good for you or not?
Yes.
Sure. Why not, right? So that would make it positive. Yeah, do that. Let me move this over. Yeah, that'll work. How about beta 3? If she's right, what direction should it be?
Is it negative?
Yeah.
We gotta vote for negative.
More forgiveness, less stress, so it.
Stress is not the outcome. Psoriasis is the outcome.
Psoriasis.
So
What a positive.
you're like an hour early, but you can come. No, a half hour early, excuse me, but you're welcome to play along. No, it's fine. No worries. That's how you know you've had a long Thanksgiving break. You forget your class schedule. I'll see you in a bit. So stress is not the outcome. The question is handling stress, mitigating stress, reducing the impact of stress. I like mitigate. Dampening stress. Is forgiveness a protective factor for stress?
Doesn't make it less negative.
Hey! Doesn't make it less negative, which would mean this coefficient would have to be positive to go less negative. Exactly. Yeah. So should I get paint out? Would that help? I think paint helps everything, right? Where did it go? Here it is. So if you had to show like a graph of expected results, that's something that is helpful for dissertation proposals sometimes. So I would do something like this is stress, this is psoriasis, and people with more stress, hang on, I think I got it this backwards. Psoriasis, stress is bad for you, but psoriasis is bad for you too. Let me back this up. Let's go with skin health as the outcome, because then this works. So we'll go with skin health. There we go. So stress is bad for you. More stress means to less health. But if you're more forgiving, maybe it's like that. And if you're less forgiving, maybe it's like that. Yeah, no wonder you guys were confused. You weren't sure which way I was going. So if this is health, that works like that. Nope, hang on. But if we went the other way, sickness, then beta 1, is forgiveness good for sickness or bad? It's bad, right? So it's good for, yeah, see, this is when things are in different directions. When more of the outcome is bad, it makes it really hard to follow. It does. So if you are more forgiving, you should be less sick, which means negative. If you are more stressed out, you should be more sick. So this is positive. And if you should be less susceptible to stress, then this is negative. So everything flips. So in this context, if we added in a covariate, right? What else do you think might be related to psoriasis severity? How long you've had it, maybe? Something like that? Let's go beta 4 times duration.
Environmental factors.
Yeah, I was thinking weather.
Weather, sure. Let's throw those in too. Why not? Plus, you guys are going to make excellent reviewer 3s someday. Did you control for weather? Because my theory says you should.
Are they treating?
Yeah, there's all kinds of stuff, right? So this would get attacked on a number of grounds here. Hang on. I'm throwing a parentheses in willy-nilly here. Let me try and make them consistent. So in terms of the language that we were just talking about, there. Which of these, so how many, let's go at the top. How many fixed effects are in my model? Six, because it's how many betas do I have? How many predictors are in my model? How many ideas, like constructs? 4, right? Weather, duration, forgiveness, and stress. So duration and weather, the ones that we just added, those are conditional or marginal? They are marginal. What's the difference?
They don't have an interaction effect. So they can't be.
They don't have an interaction. So beta 4 is the effective duration for everybody, regardless of their levels of stress, forgiveness, environment, whatever. Likewise, beta 5 is the effective weather for everybody. Now, I'd still call these unique, right? Because this is the effective duration and weather after controlling for stress and forgiveness. Likewise, stress and forgiveness effects are after controlling for these things. How about beta 1 and beta 2? Are these marginal or conditional? These are the conditional, which means it's the unique effect of forgiveness specifically when stress is 0 because of the interaction term. This is the unique effect of stress specifically when forgiveness is 0, and that's why centering matters, right? Because otherwise, beta 0, beta 1, and beta 2 would all be stupid because they are referring to 0 values that don't exist. Not wrong, but stupid. Now, how about this interaction term? Marginal or conditional? This is a tricky one. Do you see anything else in the model that has both of them together as part of another interaction, like a 3-way interaction? Nope. So what does that mean it is? It's marginal. So beta 3 is how forgiveness changes the stress slope for everybody. Beta 3 is how stress changes the forgiveness slope for everybody. If I wanted to do something like this, plus beta 6 times duration times forgiveness times stress. Could I do that? Hey, don't yell at me. No. Oh, it's confused about that. It's the beta plus. All right, let me do that. Hey, let me have it. I hate it when Word and Excel get all ruin my thing. Hang on. Go back to health. Plus beta 6 times duration times forgiveness times stress. There. Thank you. Now, could I do that? This is an advanced topic that we're not going to get to this semester. The three-way interactions? In theory, yes. Because then this forgiveness by stress interaction would be specifically when duration is 0. What was that? I give up?
Oh, no.
However, I can't do this. This is breaking a rule. I can't have a three-way interaction without having all possible two ways underneath it. So in order to test whether the extent to which forgiveness moderates stress depends on duration, that's my three-way. The extent to which, what did I just say? The extent to which forgiveness moderates stress depends on duration. That is a three-way interaction, folks. I can't say that without also adding duration by forgiveness, duration by stress. Because it's over and above. And the way I would talk about that is beta 6, in this case, makes this beta 3 two-way interaction more positive, less positive, more negative, or less negative as a function of duration. It's all algorithmic. So three-way interactions don't come along very often. People often run and hide from them. But there's nothing different than what we've already done. It's just a level of inference higher. They take the two-way interactions and adjust them as a function of the third variable. So in that case, if we had this three-way interaction and all the other constituent two-way interactions, this beta 3 term would become conditional as well, and you would refer to this as a simple interaction, because this would be the two-way interaction specifically when duration is 0. Ta-da! Linear models are fun. They're like puzzles. But this idea of being able to take general concepts and turn them into models, this takes a lot of practice, but it's really important. And being able to come up with an analysis plan that goes along with it is important too. So in this case, what are we assuming about our sampling design that allows us to use general linear models that we've learned so far to do this? What are we assuming about our patients in this psoriasis clinic? They're independent. What if they're seeing different doctors? What would I do?
Like they're seeing more than one doctor at the same time.
That could happen, or patients are nested within doctors. Like each one, there's like 10 doctors in the clinic, and a patient sees one doctor. Do you think I need to control for that?
Yeah.
So I would have two options for doing that. One is to treat doctors as a random effect, which means that's another kind of variability. I could explore why some doctors have better patient outcomes. That's multi-level modeling. I could also put in 9 dummy codes for which doctor is which and treat it as a fixed effect. And then I could see if Dr. Jones has better outcomes than Dr. Smith, for instance. So I'd have to make it so that patients are independent after controlling for doctors somehow. What were the other two? Two types of things that we have to be plausibly believable to use this type of model. What kind of quantitative outcome am I predicting? What shape should it have? Normal.
Not that one.
Not that one. Yeah, so do you think that sickness or psoriasis severity is normally distributed? Does it have to be? No, what has to be normal? Residuals. So if it were this kind, like the skewness kind, then I would want to make sure that I have predictors in the model that can account for that skewness. Otherwise, I need a different kind of model that uses a skewed distribution instead. And one more. What are we assuming about the variability across patients? Fancy H word. Heteroscedasticity or homoscedasticity? Homo or hetero? Yeah, it's in this case it's homo. It means constant variance. Because this model, at the very end here, my E has one variance. I'm going to have one mean square error, one residual variance that shows up on my output. That means logically that variance should hold for everybody. But if there are pockets of people for whom this regression line doesn't work as well, that means that having one E variance doesn't work. And so we need to add something to the model that allows different types of people to have different kinds of residual variances. Possible to do. We're not going to get there this semester. Come back some other day. All right, we're all done for today. So we'll do a little more on continuous interactions, quantitative interactions next time, and then pick up lecture 8 and example 8. How's that sound? Okay. All right, then have a good day. I will see you Thursday.